Looking at what we have been dealing with concerning polynomial functions, and last time we looked at zeros and their multiplicities, which signaled whether the graph would touch or cross the x-axis at those particular intercepts, and we had followed by the end behavior of the graph of a polynomial function. And again, we have for a polynomial function, again we have our four distinct cases, whereupon if you have the coefficient of the highest order term to be positive while the degree of the polynomial is odd, the end behavior you have down to the left, up to the right. And for odd degree polynomial functions, if the leading coefficient is negative, you have the end behavior to be up to the left and down to the right. And we have for the even degree functions, kind of like whenever we were working with quadratic functions, whenever the coefficient a is positive, you have the graph to be opening upward at both ends, up to the left, up to the right. And whenever the coefficient is negative, you have downward motion both to the left and to the right. And now we have including what we have in the descriptions of the graphs of polynomial functions in terms of pinpointing the behavior of the graph. And one of the items you have, going back to when we were looking into relative minima and maxima prior to the spring break, and we have going back to turning points. And for what we have, once again, concerning turning points, we have the number of turning points will be an odd amount. Less. That is where the difference is an odd amount. You can have an even number of turning points, but where the difference between what we're going to have for the number of turning points and the degree of the function, you're going to have the difference to be an odd amount less than the degree of the polynomial. And let's say that if we were to determine the following. And we'll say we have, first of all, looking for the number of turning points. And the end behavior. And also we have the sign of the highest order term coefficient. Okay, so we're looking for the sign of A of n. And also if n is odd or even. And also you have the possible degrees, or the possible degree of f of x. Okay. And we'll say that we have, just as an illustration, okay, so just putting in the, again, the x-axis and y-axis. And we'll say that for our polynomial function. And we have just for the items. Okay, so if we're looking at the number of turning points, okay, and this would be the combined total of the relative minima and maxima. Okay, so from left to right, okay, so you have a peak or relative maximum, okay, at the start, and then you have a relative minimum, followed by a maximum, and then finally we have another minimum, and then after that we have continuous increase in the function. Okay, so you have a combined total for minima, relative minima, and maxima. So in this case, we have 4 turning points. And for what we have regarding the end behavior, okay, so you're looking at the far left and far right. Okay, and for what we have in this case, right, so you have the extreme left, okay, you have down to the left or false to the left. And for what we have to the extreme right, okay, you have moving upward, okay, say up to the right or rises to the right. Now for the sign of the leading coefficient, okay, now if you notice the end behavior, you have down to the left, up to the right, and where we have down to the left, up to the right, it's going to follow that the coefficient a of n is positive, and also the degree value of n is going to be an odd number. Again, so we have a of n is positive and n is odd. And for the possible degree of f of x, okay, so you have, so for the possible n values, okay, so you have an odd amount, okay, and it is going to be greater than the number of turning points. Again, so we have 4 turning points. So when n is odd, we cannot include 1 or 3 since that is less than the number of turning points. So whatever value for the degree we have must be greater than the number of turning points. So we might have, it could be 5, and if it's not 5th order, then it will be 7th order or some other value. So if it's not 5th order or 7th order, it'll be some other higher odd number. Okay, so this is what we have for this particular polynomial function. Okay, now, and let's say that If I have one, nature of this is going to be different. And we'll say we have sort of creating a bit of a wave pattern. And for this function, f of x, okay, so if I count up the number of turning points, okay, so you're going to have relative maximum, then a minimum, and you can have alternating relative minima and maxima. And so in this case, we have a combined total of 7 turning points. And for the end behavior, okay, as the graph illustrates, you have down to the left and also down to the right. And looking at whether the sign value of a of n is positive or negative, and whether n is odd or even. So you got your end behavior, okay, down to the left, down to the right, and this is the last of the 4 stated possibilities. In this case, we have a of n is going to be negative, and n is going to be an even value. And for what we're going to have for the possible degree values, okay, so in terms of what n could be equal to, okay, so again, n is going to be an even amount, okay, and it has to be an even amount, okay, that is greater than the number of turning points. Here we have 7 turning points, so the minimum degree that we could have for this polynomial function is going to be 8, but if it is anything else, it's going to be 10 or some other even value that is higher. Okay, so this is what we have with end behavior, okay, concepts tied in with what we have for turning points and the determination of possible degrees. All right, and then linking with what we have had with zeros and multiplicities. And we have from what we have in the case of section 2.2, and we have just for the group of problems, and we've got see if I can, yeah, here we go. Okay, for this item, okay, that we have in number 48, okay, it says to determine the minimum degree of the polynomial, okay, and determine whether the leading coefficient is positive or negative based on the end behavior, and whether the degree is odd or even. And then you have approximating the real zeros of the function and determining if the multiplicities are even or odd. Okay, so just some things here that we have just fresh off of these examples, okay? Like if we were to determine the number of turning points, okay, so you have, let's So the graph starts out by dipping, then you have rising to a relative minimum, and then we have getting to the x-axis at 3, 0, where we have that to be the second relative minimum. And okay, so for what we have here, for this function, we have 3 turning points. And we have for the end behavior, okay, you have up to the left, up to the right. Okay, so you got 3 turning points. In behavior, you have up to the left, up to the right. And since we're looking at the set of items concerning the zeros that we have here, so we have on the x-axis case, you have at x equal to -4. Okay, so here we have the graph is going to cross. And we have at x equal to -1. Okay, the graph also crosses the x-axis. And once we get to x is equal to 3, okay, we're going to have the graph to touch. Okay, and now for what we have in the case of just for the mechanics involved, so we've got 3 turning points. In behavior, you have up to the left, up to the right. And again, just for the in behavior, whenever you have up to the left, up to the right, okay, the leading coefficient A of n is positive, and the value of n is even. Okay, now for what we have in terms of the minimum degree of the polynomial, okay, so for what we have in part A, for the minimum value of n, okay, that is going to be even, and it's going to be the smallest even number higher than the number of turning points. So we had 3 turning points, and so we have for the minimum value of the degree, okay, that is going to be at 4. And we have in the case of part B, okay, determine whether the leading coefficient is positive or negative based on the end behavior. And again, we already had this laid out. Okay, so you have A of n is positive. And whether the degree is odd or even, okay, we've already laid this out. And in the case of what we have for the zeros of the function, and whether the multiplicities are even or odd. Okay, so we have in the case of the zeros, okay, so you have x equal to -4. You also have x equal to -1. Then we have that x is equal to 3. All right, and for what we have in the case of the multiplicities, okay, whether the multiplicity is odd or even. Okay, so I'm just going to do a little bit of color coding. Okay, so you have crossing of both x equals -4 and x equals -1. Okay, since you have to cross. So these zeros will be of odd multiplicity. Then we have, on the other hand, okay, with x equal to 3. Okay, so that location, okay, the graph touches the x-axis, and x equals 3. Okay, this 0 will be of even multiplicity. Okay, and we still don't know specifically what this polynomial function is, but we have a good general idea in terms of some of the possibilities. Okay, since it is going to be at least a fourth order polynomial, and we know that the leading term or highest degree term is positive, and that it's going to be an even degree function. Okay, and now in the case of what we have for polynomials that are specified, where we were looking at finding out how these are going to appear along the lines of graphing, and we have for the next set of items, and we have with the case of for number 59, and we have just for the set that we have here. See if I can. Okay, so we have for this exercise set, it says to sketch the function. Okay, and for what we have in the case number 59, we have the presentation whereupon the polynomial is an expanded form. Okay, so part of the process, we can go ahead and identify the zeros and their multiplicities and be able to determine where the graph is going to cross as well as touch the x-axis. Okay, so we have transitioning from the expanded to the factored form. So for x cubed minus 5x squared, we're going to have the greatest common factor in the difference to be x squared. And upon factoring out x squared, we have times the quantity of x minus 5. And just rewriting this, whereupon I'm just going to specify or highlight the degrees. Okay, so again, I have x to the second. And we have implicitly from the factor form, we have x minus 5 is to the first. Okay, and so looking at the zeros, and we have in the case of the x factor, we have x is equal to 0, and from the x minus 5 factor, we have the x is equal to 5. And in the case of the multiplicity, again, multiplicity of 0 is the degree to which the factor corresponding to that 0 will be raised. Okay, so 0 has a multiplicity of 2, whereas 5 has a multiplicity of 1. And whether the graph crosses or touches the x-axis. Okay, so here we have, for x equal to 0, you have an even multiplicity. Okay, so this is going to touch at x is equal to 0. And since x equals 5 has a multiplicity of 1, and with 1, being an odd amount, okay, this one is going to cross the x-axis at x equal to 5. So we have transitioned from the expanded to the factored form and have identified the zeros. And for the activities in between where we have crossing and touching the x-axis, we have a couple of cases here. Now, looking at the components that will lead us to determine the end behavior, and just looking at the expanded form, once again, so you have x cubed minus 5x squared. Okay, and we have the terms laid out in descending degree order. So the first term is the highest order term. Okay, so that's going to be x cubed. If I want to spell out the coefficient, okay, you see we have 1x cubed. Okay. All right, and so we have for the highest degree term coefficient, okay, have a of n is equal to 1. Okay, so that is positive. And from x cubed, okay, we have that n is equal to 3. Okay, and for positive terms, as well as where the degree is odd, okay, we will have for the end behavior. Okay, again, this is going to be down to the left and up to the right. Okay, now another feature in terms of graphing, okay, and Alex often emphasizes this, okay, now, you notice, okay, the zeros we have, okay, those are our x-intercepts, and again, intercepts will be locations whereupon the graph crosses or touches the x-axis. And also another item, okay, we have stressing any potential y-intercepts. Okay, and for the y-intercept, again, you're looking at solving for y as x is set to 0. So for your y value, okay, we're looking at f of 0. Again, we have x cubed. Again, that is the cube of 0. And we have minus 5 times the square of 0. Okay, so I have 0 cubed is 0, 0 squared is 0. And so the y-intercepts we're going to end up with, okay, this is already one of our x-intercepts, which we have to be the origin. Okay, and for what we have in terms of laying the bricks upon the foundation. Okay, so for the items of interest, okay, so we have with our intercepts, okay, so you have x equal to 0. Also we have x equal to 5. And again, our y-intercept is the origin. And for what we have in terms of the activity, okay, so we got all the intercepts laid out. Now, for the end behavior, you have down to the left and up to the right. Okay, and we can illustrate down to the left and up to the right. Okay, so down to the left, we can have downward motion. Okay, from the leftmost zero case, which so we have at the origin. So you have motion. So you have down to the left. And for up to the right, okay, so we have from the rightmost zero. In this case, where we have x at 5. So you have up to the right. And for the activity that we have to occur in between, okay, so we have at 0 and 5. So at 0, now the graph is going to touch. And once we get to x equals 5, we're going to have the graph to cross. Okay, so filling in the empty space. Okay, so reading in order from left to right. Okay, so from down to the left. Okay, so in terms of rightward motion, okay, we have rising up and getting to the x-axis where it is going to touch or essentially bounce off the x-axis, and then there will be a relative minimum, and then you're going to have the graph to increase, and this time it is going to cross the x-axis at x equals 5. And for the rest of the activity, okay, you have moving up and out to the right. So this is what we have in the case of the general dynamics for f of x is equal to x to the 5th minus x cubed. Right. Now, for what we have in the case of the next item, and now the nature of this one will be very similar. And so for what we have now, in the case of number 60, okay, so this time we have in the form where we have y is represented by g of x, and this is also expressed in expanded form. So if I go from expanded to factored form, so I can identify the zeros as well as their multiplicities. Okay, so this time we have for the difference of the terms, we have the greatest common factor. Okay, it's going to be x to the 4th. And here upon factoring out x to the 4th, okay, we have the factored form for g of x, where we have x to the 4th times the quantity of x minus 2. Again, just rewriting and stressing the degrees. So I have x to the 4th times x minus 2, okay, which will be to the 1st. Now looking at identifying the zeros. So we have the x factor once again. So you have x is equal to 0. And from x minus 2, if x minus 2 is equal to 0, okay, so I have that x is equal to 2. Right. And again, for 0, okay, because the corresponding factor is raised to the 4th degree, okay, we have the multiplicity at 4. And for x equal to 2, this stems from the first order of x minus 2, so we have a multiplicity of 1. And so for the even multiplicity, okay, zeros of even multiplicity will be locations whereupon the graph will touch the x-axis. And for what we have here, okay, we have touching at x is equal to 0. And again, for zeros of odd multiplicity, okay, you have to be crossing. Okay, so crossing at x is equal to 2. And we can go ahead and arrive at the end behavior. And again, just for the highest degree term, again, you'll have this time x to the fifth. Okay, so you have the first term to be the highest order term. And for what we have here, so we have for a of n, again, that is equal to 1. So that is going to be positive, okay, and we have for the degree n is equal to 5, which is an odd value, and we have in the case of the n behavior, say EB for n behavior, again, we're going to have, just like number 59, you're going to have down to the left and up to the right. Again, just for the y-intercept, okay. This is a bit repetitive for this particular function, since we're going to have the origin, once again, and the origin we already have as the first of the x-intercepts. But just to kind of mention, we have g of 0, so we're looking at 0 to the fifth. Minus 2 times 0 to the fourth. So you have a difference of 0 values. Okay, so the y-intercept we have at y is equal to 0. And so we have at 0, 0. Okay, and just referencing everything, okay, in behavior as well as the intercepts and the activity that will occur between and outside of those intercepts. Okay, so we have with our intercepts, okay, so you have x equal to 0. You also have x equal to 2. And again, the y-intercept is the origin. For the end behavior, again, we have down to the left, up to the right. So you have this occurrence once again. So you have down from the leftmost 0. And at the other end, you have up to the right. So you have upward motion to the right of x is equal to 2. And for what we have in between, okay, so you have the graph touches the x-axis at the origin, and once we get to x is equal to 2, the graph is going to cross. And so just following through, so you have from left to right, so you have getting to the x-axis, and you have touching at the origin, then you have kind of dipping to a relative minimum, and then you have an increase in the function, and we have crossing at x is equal to 2. So we have the dynamic to play out for f of x is equal to x to the fifth minus 2x to the fourth. Okay, so there's a lot of similarity between the behavior of the graphs in numbers 59 and 60. You had the same end behavior, 2 zeros first you have to touch, and the second to last you have to cross. And now for the next one, okay, you're going to have a change up in terms of the behavior. And we have for 64, and this time we have going out to where we have y is equal to h of x. And we have not just one term, but three terms that will define h of x. And if we look at going from the expanded to the factored form, so for x to the fourth, negative x cubed and minus 6x squared, okay, the greatest common factor will be x squared. And upon factoring, okay, so we have x squared minus x minus 6. And for the second order trinomial, I can factor. So I have x squared. And for the linear factors of this trinomial, okay, so I have x, and what's going to be minus 3. And on the side of addition, we have x plus 2. So this will be the factored form. Okay, and again, just stressing the degree, so we have x to the second. And we have x minus 3 is to the first. And again, we have the quantity of x plus 2, which is also to the first. And we have with the variable factors, okay, again, so we have x. So we have x is equal to 0. And for x minus 3, we have x is equal to 3. And for x plus 2, okay, now we have that x is equal to negative 2. Okay, now for the multiplicity values, okay, so we got 2 for the first 0 and 1 for the other 2. And we have at x equals 0 because of the even multiplicity. Okay, so the graph is going to touch. At that location, and for x equal to 3 and x equal to negative 2, okay, the graph is going to cross. And for what we have for h of x, once again referencing the expanded form, okay, so you have f of x, again, so we have x to the fourth minus x cubed minus 6x squared. Again, highest degree term. Let's say HDT for short. Okay, so x to the fourth, or 1x to the fourth. Okay, so for the coefficient a of n, okay, so you have 1, which is positive, and we have the degree n to be at 4. So you have an even value, and whenever the degree of the function is even and the highest order term is positive, okay, that means that for the end behavior, okay, you have moving up on both ends. So moving up to the left and up to the right. And again, just for the y-intercept, I'll just mention as a quick rule of thumb, you don't have to do this if you already have the x-intercept, okay, to include the origin, because the y-intercept, unless if there happen to be two y-intercepts, but for this type of function, you're not going to have it. So in this case, you have y is equal to h of 0. So you have 0 to the 4th minus 0 cubed minus 6 times 0 squared. So all these terms are negligible. And once again, we had the y-intercept to be at the origin. Okay, now in terms of the dynamics, that we have for h of x okay, and this time we have a trio of distinct zeros in x. Okay, so you have x at 0, also you have x at 3, and x at -2. And again, you have the y-intercept is the origin. And now for the end behavior, you have up to the left and up to the right. So you have up to the left from the leftmost 0, in this case, away from x equals -2. And up to the right, away from the rightmost 0, which we have at x equal to 3. And filling in, okay, the empty spaces. Okay, so we have, again, at x equal to -2, okay, now we're going to have the graph to cross. And we have at x equal to 0, okay, the graph is going to touch. And once we get to x equals 3, okay, we'll have the graph to cross. Okay, so just looking at what we have within these parameters. Okay, so from left to right, so moving downward, and the graph crosses the x-axis as we get past x equals -2, then you're going to have it to rise. And once we get to the origin, it's going to touch. It's going to dip once more and start to increase. And once we get to x equals 3, okay, the rest of the graph is going to be above the x-axis. Okay, so this will be what we have in the case of this particular polynomial function. All right, and so far for these cases, okay, the y-intercept, okay, has been the origin. But for what we have in number 72, okay, that particular streak will come to an end. And so we have for the item, okay, for number 72, okay, and this one, a little different one in the sense that we have a negative leading term in the mix. Okay, and so we have with y in the functional notation represented by h of x, again we have expanded notation, and I can convert, okay, to the factored form. Okay, and what I'm going to do here to make this factor friendly as much as possible. Okay, notice the leading term is a negative, x to the 4th. So I can factor out -1 or factor out the negative sign. Okay, so for h of x, I can write this as the opposite sign of x to the 4th minus 10x squared plus 9. And here we have factorable trinomial expression. Okay, so upon factoring out the negative, okay, so we have with x to the 4th I can factor out to x squared and x squared. And for factors of positive 9, that will combine in terms of adding to negative 10. And we have, in this case, a minus 1 and a minus 9. And if you notice, okay, the second order terms or expressions, okay, those are differences of squares. And so I can factor even further. Okay, so for x squared minus 1, okay, so this will factor out to x plus and x minus 1. And for x squared minus 9, okay, this will factor out to x plus and x minus 3. All right. And again, if I stress the degrees, okay, since there are no explicitly raised powers, all these variable factors in x, okay, will be to the first power. Okay, and so for the zeros, okay, so from x plus 1, okay, I have x equal to negative 1. For x minus 1, okay, so I have x is equal to 1. For x plus 3, okay, so I have x equal to minus 3. And for x minus 3, I have that x is equal to 3. Okay, so now with the multiplicities, okay, so got all of these will have multiplicities of 1. And in terms of whether the graph crosses or touches the x-axis, okay, and in this particular case, it's going to cross at all 4 of these zeros. Okay, so there are no zeros, okay, where we have just touching the x-axis. So you have crossing throughout. And for what we have for h of x, now looking at the end behavior, and we have with the highest degree term, okay, so you have negative x to the 4th, or minus 1x to the 4th. And again, just with the leading coefficient, okay, so you have minus 1. So you have a negative, and for the degree in n, okay, we have 4. And that is even. So with the combination of the leading coefficient as a negative and with the degree of the function as an even value, okay, we'll have for the end behavior this time, you will have down to the left and down to the right. And this time for the y-intercept. Now this is going to be distinct from the origin. And for the y-intercept, okay, so here we had that y is equal to h of x, where x is 0, so you have h of 0. And so we have for y. Okay, so you have 0 to the fourth is 0, 0 squared is 0, 10 times that is still 0, and we have the negative 9 to follow. So this time, instead of y is equal to 0, we had the y-intercept to be y is equal to negative 9. And just displaying in ordered pair terms, okay, would come out to 0, negative 9. Okay, and okay, so looking at the tools at hand. Okay, so we got 4 distinct zeros, 1 y-intercept, and we have the identification of the end behavior. Okay, so we have with our zeros, okay, so you have x at negative 1, x at positive 1, also we have x at negative 3, and y at positive 3, and for the y-intercept, okay, you have y at negative 9. Okay, and now for the end behavior, again, you have down to the left and down to the right. Okay, so you have down to the left from the leftmost 0. And down to the right, you have downward from the rightmost 0. Rightmost 0 being at x is equal to 3. And for the items in between, okay, and we have throughout at negative 3, as well as negative 1 and positive 1, and x at positive 3. We're going to have crossing throughout. Then we have for the follow through. Okay, so from left to right, so you have going up, crossing the x-axis, it's going to reach a relative maximum, and then cross. It's going to start to dip, okay, and then you have going through the y-intercept, and somewhere it's going to rise. And we have to cross the x-axis at x is equal to 1. And it's going to reach another relative maximum, and then start to descend, and it's going to cross at x is equal to 3. So this will be the general behavior of what we have for this particular fourth order polynomial function. Okay, and again, this is not drawn to scale, but in terms of how this will interact with directly with respect to the x-axis as well as the y-axis, and for the extreme end behaviors, okay, this will be in line with what we have for f of x. Okay, and now in the crossover to what we have in section 2.3, and this is what we're going to have concerning polynomial division. So we're still working with polynomials, but we're going to cross over to the operation of division. Okay, and for what we have in the case of polynomial division, okay, and let me give you a case here. Okay, so you have with polynomial division, okay, and let's say we have something like and just like in numerical division, you'll be looking at quotient and remainder. Okay, first of all, okay, for the first round, we'll be looking at cases of long division. And let's say that if we have, let's see, we have x squared plus 4x plus 9, okay, is divided by, let's say we have x plus 1, okay. And for what we have in the setup, okay, so if we go with the long division route, okay, so you're looking at taking x plus 1 into x squared plus 4x plus 9. Okay, and now you want both sets of terms to be in descending degree order, and you don't want any missing degree terms. And if you do, you will just use 0 for the placeholder. Okay, so we got x plus 1, and then we have for x squared plus 4x plus 9, you got the second order, first order term, as well as closing out with the constant. Now for the quotient, you're looking at how many times x plus 1 will go into x squared plus 4x plus 9. So if we look at the first terms of each, so you have x from x plus 1, x squared from the trinomial, and if I take x into x squared, or x squared divided by x, okay, this will leave us with x. Okay, and in terms of what to do with x times x plus 1, so this will be x squared plus x, and this product will have these terms situated underneath the like terms from what we have with x squared plus 4x plus 9. So you have x squared under x squared, x situated underneath 4x. And now with long division, you're going to be looking at row by row subtraction. And the object at each stage is to get out the leading term from that which originates from what is referred to as the dividend. And the dividend being x squared plus 4x plus 9. So we have with, okay, so we got x times x plus 1, so we got x squared plus x. And subtracting the corresponding parts. Now we'll have x squared minus x squared, that goes out. And now we have 4x, and what's going to be minus x. So that's going to leave us with 3x. And then we have, now we can bring down the plus 9. 9 has not been touched yet, so we just bring that down. Okay, so I took initially x into x squared, and after the first round of long division, okay, so I'm down to 3x plus 9. And I can now take x into 3x, which will go 3 times. And we have with distribution. So we have 3 times the quantity of x plus 1. So this will be 3x plus 3. And we have for subtracting, once again, so 3x now goes out, and we have 9 minus 3. Okay, so this will become 6, and this will be as far as we can go in terms of the complete process of dividing. For I could take x into x squared, x into 3x, but I cannot take x directly into 6. Okay, and so for what we will have in this case, okay, we will have for the quotient, this will be what we have at the top. How much x plus 1 goes into the trinomial, so you have x plus 3. And the lagging number 6, okay, that is going to be the remainder. and for the ratio. And I know Alex likes to have the ratios expressed in both quotient and remainder over divisor terms. So for x squared plus 4x plus 9 all over x plus 1. Okay, so again you have the quotient, which you have at x plus 3, and for the remainder over the divisor. Okay, so we have x plus 3, and then we have plus 6 all over x plus 1. And just on a parallel note, it's kind of like if you take, say, like have 3 taken into 100, like 3 without going over, 3 will go into 100 33 times. And 33 times 3 is 99, and 99 taken away from 100 leaves us with 1. And so you would have 33 for the quotient, remainder would be 1, and like 100 thirds would be like 33 and 1/3. Same parallel note, but with the variable x involved. Okay, now, and let's say that if we have a scenario, and we'll say that we have, let's say we have x cubed plus 4x squared plus 5. And we'll say we have this to be all over x minus 2. Again, if we look at this through long division. Okay. So we have here, so you got x minus 2. What you're taking into, that is the divisor, and what you're taking into the dividend. Okay, so you have x cubed plus 4x squared. And notice we don't have a first order x term, but I want the first order to be represented in the process. Okay, so we'll need a 0 placeholder. Okay, so you have 0x. And finally we have the dividend to close out with a constant. And if I had only x cubed plus 4x squared, I would have closed out in the dividend in the long division setup with 0x plus 0. All right, now, so initiating the process. Okay, so got both sets of terms in descending degree order. Okay, and taking the leading term x into the leading term of the dividend x cubed, so, or x cubed divided by x. So this time the first term in the quotient will be x squared. And we distribute, so you have x squared times the quantity of x minus 2. So you're going to have x cubed minus 2x squared. Then we'll line up these terms underneath the like terms from the dividend. So I've got x cubes lined up, and negative 2x squared situated underneath 4x squared. And looking at what we have with, after undertaking the first round in the division case, you have subtracting, so you have x cubed minus x cubed goes out, and we'll have 4x squared, and what's going to translate to plus 2x squared, and so we're going to have 6x squared. I can bring down the 0x and the 5. And again, the 0x and the 5 have not been touched, but in the next step, at least the 0x will interact with the last product that we have in the multiplication of x minus 2 and what we have for the second term of the quotient. So we have already took x into x cubed, now taking x into 6x squared, or 6x squared divided by x. So this will be 6x So you have 6x times the quantity of x minus 2. Okay, so you have 6x squared minus 12x. And subtracting. Okay, so 6x squared goes out. Then we have 0 minus negative 12x. And again, subtraction of a negative translates to addition of the positive. So you have 12x. And just bringing down the 5. Okay, so we got x. I can now take into 12x, and this will go 12 times. Again, just on the side here, so I got 12 times the quantity of x minus 2. Okay, so 12x minus 24. And applying the subtraction once more. So I got 12x minus 12x will go out, and 5 minus negative 24. Okay, this will translate to 5 plus 24. And so this will come out to 29. Okay. Okay, so we have, in the case of the quotient, okay, so we have x squared plus 6x plus 12. And since I cannot take x directly into 29, okay, 29 is going to be the remainder. And just putting in terms of expanded quotient plus remainder over divisor notation. Okay, so for this ratio, okay, we have with the quotient, so you have x squared plus 6x plus 12 and then we have plus 29 all over x minus 2. All right, and tell you what, just for what we have, a little bit of a special case. Tell you what, for determining the quotient and the remainder, let's see what we get whenever we have 7x to the 4th plus 2x squared plus 1 all over x minus 1. Now I'll kind of use this example as a springboard to the other type of division between polynomials with what we will have with synthetic division. Okay, but just for the next few moments through line division, let's see what we get for the quotient and the remainder of this ratio. All right. Just for this ratio, okay, just some of the additional terminologies. Okay, so we're looking for the quotient and remainder of this particular ratio. And now for the binomial x minus 1, that which you're taking into, okay, this is going to be what is referred to as the divisor. And for what we have in the numerator, that which is being taken into, okay, this is what is referred to as the dividend. And looking for the quotient and remainder, okay, for now, through the use of line division. Okay, so you have with the divisor into the dividend. Okay, so you have x minus 1. And we have taking into the dividend. Okay, so we have the first term, highest order term. Okay, we have 7x to the fourth. Notice that the next term is 2x squared. Okay, so we're missing a cubic term, so I want to use an x cubed 0 placeholder. And then we have plus 2x squared. And notice I'm missing a first order x term, so I'm going to use 0 once again for placeholder purposes. Yeah, followed by the addition of 1. Okay, so for what we have in the initial setup, okay, so we have both the divisor and the dividend. We have in descending degree order. Okay, so just as in the earlier cases, I can take first term from the divisor into that of the dividend. And here we have x into 7x to the fourth. Okay, so 7x to the fourth divided by x. Okay, so that's going to be 7x cubed. And again, if I were to multiply 7x cubed and x minus 1, so you have 7x to the fourth minus 7x cubed. And subtracting from the like terms from the dividend. Okay, so you got 7x to the fourth goes out, and we'll have 0x cubed minus negative 7x cubed. So this would change over to addition. Okay, so we have 7x cubed plus 2x squared plus 0x plus 1. Okay, now I can take x into 7x cubed, and this will go 7x squared times. Okay, and so you're going to have the first product is going to be 7x cubed. Now just, again, working to the side. Okay, that is optional, but just taking what we have now. So got 7x cubed minus 7x squared. So I'm going to place this directly underneath the like terms that have spun off from the dividend. Okay, so here we have 7x cubed terms will go out. Now we got 2x squared minus negative 7x squared. So this will change over to adding. So this will become 9x squared plus 0x plus 1. Now we have x into 9x squared. So we have 9x times. Okay, so we distribution. So we have 9x squared minus 9x. And distributing subtraction once again. So 9x squared terms will go out, and 0 minus negative 9x translates to adding. Now we have x into 9x. So this will go 9 times. Now we have with subtract, so 9x terms will go out. 1 minus negative 9, this will change over to 1 plus 9, which will be 10. And unlike 9x, 9x squared, 7x cubed, and 7x to the fourth, I cannot take x minus 1 directly into 10, and that's going to end up as the remainder. Okay, so just looking at what we have now, the quotient. Again, we have this cubic expression, so you have 7x cubed plus 7x squared plus 9x plus 9. And we have that the remainder is going to be at 10. And just providing the expanded notation, so we got the quotient. So we got 7x cubed plus 7x squared plus 9x plus 9. And then we have with the remainder, we say we have plus 10 all over x minus 1. Okay, and now for we're going to have, in the case of transitioning from long to synthetic division, okay, and for a polynomial, again, it's kind of going back to the theoretical notation, like when we were looking at in behavior. We have a polynomial, okay, divided by a binomial expression that is linear. Okay, and we have for this in case you have divided by a binomial expression, in case you have x minus c. Okay, first of all, okay, we have the long division setup. Okay, so we have x minus c as the divisor. Again, we have taking into the dividend, so you have that polynomial. Just like what we were doing earlier, but with specified numerical expressions. Okay, now let me mention, okay, so we have the long division setup, so x minus c is the divisor. Now, going back to looking for zeros, okay, so you have the divisor is x minus c. Now, for what's going to be synthetic division, okay, representing the divisor, I'm going to be taking the 0 of that divisor, which we're going to have with x is equal to c. And if this is the long division setup, we're going to have what's referred to as the synthetic division. Now for this arrangement, okay, so we have like boxed or isolated. And the notation, Alex, or at least in terms of the construction will be kind of different. But anyway, you're going to have C isolated. And across from C, okay, you're not going to see the x terms, but instead you're going to see the numerical coefficients, like a of n, and that should be a of n minus 1. All the way out to a naught. And let me mention, okay, now to use synthetic division, to use it directly. The divisor must be in the form of x minus c where the x is of first degree. I was kind of give you kind of like highlight some cases here, like if you got your divisor, and let's say if you have a divisor, okay, we'll say we have x minus 3. Can synthetic division be used directly? And it can be. And if we have, let's say, x plus 2. Okay, now the minus, in the general case, like minus c, like addition of a constant could be translated like to subtraction of the additive inverse, okay? And x is still the first order, so that is going to be yes. And let's say that if I have a case, let's say if I have x squared minus 5, again, because we have second degree in x, I cannot use synthetic division directly. Okay, so you must have it where x is a first order. Okay, now when we had looked at this particular polynomial, okay, 7x to the 4 plus 2x squared plus 1 divided by x minus 1, and I think I can get, I'm trying to get this copied. It might not transfer, but you won't know unless you try. Yes. Okay, so just going back to what we had earlier. When we looked at this example. Okay, now you got your line division set up. Okay, again, you had the divisor x minus 1, and then you got your polynomial dividend, and again, you're using placeholders. Now, for what we will have in terms of the synthetic division setup, okay, now representing x minus 1, you'll be taking the 0 of x minus 1, which we would have at x equal to 1. Okay, and for the synthetic division setup, what's going to happen here? Okay, so you have by itself, you had the constant 1, the 0 of the divisor, so you got 1. And on the other side, okay, you want to put in the constants. Okay, so you got 7 for x to the 4th. And if you have missing terms in the dividend, you're going to have to use 0 placeholders. Okay, so this is going to be your synthetic division setup. Now, in terms of operating, okay, so got 70201. And where synthetic division can be used, it'll save a lot of working space. And instead of row by row subtracting, I'll be looking at column by column addition. Okay, so in terms of initiating, say I have 1 boxed in, and I'm not going to do anything with 1 right yet, but looking at the 7 from the dividend, I'm going to bring this down. Okay, so bring down 7, and what's going to happen here is that whatever I bring down along each column, I'm going to multiply by 1. So bring down 7. Got 1 times 7 is 7. And the product I'm going to bring over to the next column. And here I got situated underneath 0. 0 plus 7, also 7. And then I got 1 times 7 is 7. And this will be brought underneath the 2. Adding together, I got 2 plus 7 is 9. And then I have 1 times 9 is 9. And then we have 0 plus 9 is 9. And then we have 1 times 9 is going to be 9. And 1 plus 9 comes out to 10. Okay. And for what these bottom numbers will mean is that for the last column total, that's going to be the remainder. Which is going to be 10. And for the numbers in front, these would be the numerical coefficients of what we have for the quotients. And for just one round of synthetic division, okay, the bottom row figures, okay, will be representing a polynomial that will be 1 degree less than the original dividend. So as I'm bringing down this 7, we're transitioning from 7x to the 4th to 7x cubed. And we have plus 7x squared plus 9x plus 9. Okay, and to kind of give you this remaining example, okay, of what we have with determining the quotient and the remainder. Okay, so if I'm using synthetic division to find the quotient and remainder, and we'll say that we have 2x to the fifth plus 4x cubed is divided by x plus 2. Okay. Now I'm still going to use synthetic division, okay, but I'm just going to use, kind of just give you a visual in terms of the long division setup. For the long division setup, okay, again, your divisor, we have at x plus 2. Notice for the dividend, okay, you have rather high order polynomial expression. So you got 2x to the fifth. Okay, notice we do not have an x to the fourth term, so we use 0 for placeholder purposes. And then I have 4x cubed, but notice we have missing. We have second order, first order, and a missing constant term. So I had to fill those in with 0 placeholders. So you got 0x squared plus 0x plus 0. So this would be your long division setup. Now, setting things up along the lines of synthetic division. Again, so if you have like x plus 2 is equal to 0, we have that x is equal to negative 2. And we'll have by synthetic division. Okay. Okay, so we have isolate, so I have negative 2. On the other side for the column headings, referencing the dividend. So I got 2 for 2x to the fifth, 0 for the missing x to the fourth, 4 for the x cubed, and we have remaining three zeros for the missing square, first order, and constant terms in the polynomial, or from the polynomial. Okay, so again, just for the round, so your 0 we have at negative 2. Now for the first coefficient in the dividend, so I'm going to bring down 2. All right, once that is brought down, and then multiply by negative 2. So I got negative 2 times 2 is negative 4. And we'll add the terms in the second column. So we have 0 plus negative 4 is negative 4. Once that's brought down, multiply by negative 2. Negative 2 times negative 4 is a positive 8. Then we have 4 plus 8 is 12. Now, we multiply by negative 2. Negative 2 times 12 is negative 24. Adding 0 plus negative 24 is minus 24. Then we have negative 2 times negative 24 is a positive 48. And we got 0 plus 48 is 48. Then we have finally negative 2 times 48 is negative 96. And for the last column total, okay, we have negative 96. Okay, so again, bring down the leading coefficient from the dividend and just multiply by the 0. Negative 2 times 2, negative 2 times 4, times 12, and so on. And we have with the last column total. Okay, we have for the remainder, okay, that is going to end up at negative 96. And for what we have in the quotient, again, the dividend was at 2x to the fifth, but once I bring down the 2, that 2 is going to represent the first term in the quotient, which would be 1 degree less than the dividend. So this time we'll have 2x to the fourth, and we have minus 4x cubed and we have plus 12x squared. And then we have minus 24x and finally we have plus 48.